Hello and welcome back. Today we're going to talk about writing and naming formulas for acids and bases, specifically acids. Bases are all pretty much the same. So by the end of today, you'll be able to write acid formulas. If I give you the name, you'll be able to write the name given the formula, and you will be able to describe the three different theories and ways we classify acids and bases. So let's get started. First off, there are two types of acids that we deal with. The first one is called a binary acid, and the second one is called an oxyacid. So these are the two types you'll encounter. Binary acids are acids, the bi means two. So binary acids are acids containing two elements. Typically, it's a hydrogen and then an element that's more electronegative than that. So a hydrogen and a nonmetal. For example, your hydrogen halides, HF, HCl, HBr, and HI, these are all acids. This is hydrofluoric, hydrochloric, hydrobromic, and hydroiodic. When you name them, so steps to name. So for example, HF. Step 1, place hydro at the very beginning. So you start with hydro. So if I have hydro, use the root word of the second element. So hydro, and this is fluorine, so Fl. So fluor is your root. Instead of INE, we're going to change it to IC. So this is going to be hydrofluoric acid. That's HF. That's down here. We also have HCl. So hydro is the first part. The root word is chlor and end in IC. It's hydrochloric, hydrobromic, hydrosulfuric, and hydroiodic. Those are all binary acids. That's a look at how you go about naming them. When we talk about oxyacids, so binary again had two elements. Oxyacids have three typically, three or more. So these are acids containing hydrogen, oxygen, and a third element. So these are, I guess, they're all three elements. That you have hydrogen, oxygen, and some sort of third element, and typically it's a nonmetal. This is where your polyatomic ions come in very handy. If you know your polyatomic ions, naming oxyacids won't be a problem. In order to make something an acid, make your polyatomics an acid, we add H's, hydrogens to the front in order to make it neutral. And then all of your 8 ions become ic acids, and all of your 8 ions become us acids. So we'll look at some examples of this. So for example, let's start with sulfate, because it's here. So sulfate is SO4 with a -2 charge. In order to make, so step 1 is add H's, hydrogens to the front in order to neutralize. So again, hydrogen's got a charge of +1. So because sulfate is -2 and hydrogen is +1, when we cross and drop, we know that we're going to need 2 hydrogens to make it neutral. So this is going to be your formula for sulfate as an acid. And because sulfate ends in 8, it's going to become an ic acid. So instead of hydrogen sulfate here, this is going to be sulfuric acid. And one of the ways I like to remember these is 8 ions. So when I ate something, how was it? It was icky. So if you ate something, it becomes icky for your polyatomic. So if you know your polyatomic names end in 8, the acid is going to end in ic. So sulfate becomes sulfuric, nitrate becomes nitric, phosphate becomes phosphoric, which is a little bit different. Carbonate becomes carbonic. Chlorate is chloric, perchlorate is perchloric, permanganate is permanganic, acetate is acetic, and iodate is iodic. So all your 8 ions become ic acids. Your 8 ions become us acids. So this is one's a little backwards as far as my logic. But if somebody asks you about you and your partner, and you tell them, hey, somebody asked about us, and they say, okay, what'd you tell them? I said, we ate. Maybe not a good thing to say, but it's a way to think about it, that if us is I, then we can go from ions to acids. For example, Nitrite becomes nitrous acid. Sulfite becomes sulfurous acid. Phosphite becomes phosphorus acid. Hypochlorite is hypochlorous. Chlorite is chlorous. And those are your, that's kind of my naming way to remember the names is there. So these are some common names. On the left here is your formula. So if you can look, so for example, CH3COO with a negative sign is acetate. We added an H at the end. So this is one where you don't add the H at the front, it comes at the end. Or you can write it as HC2H3O2. Those are both the same thing. CO3 is carbonate. This is carbonic. Iodic comes from IO3, which is iodate. ClO is hypochlorite, so this is hypochlorous acid. But here's a list showing you all of your not all of them, but a large majority of your polyatomics and the associated acids that they become. I'll give you a chance to work through and name these different acids. If you would pause your computers at this point, pause your screens at this point so I can keep going. I'll give you the names here in a second on the next slide. So as you're moving on, these are your associated these are your names of the acids here, yes. So HI is hydriodic, HCl is hydrochloric, and so on and so forth. So you got names here and you have formulas over here to check yourself. So there's some practice for you. And then when we talk about acids and bases, when we get these terms acids and base, there's three ways that we can identify or classify them as an acid or a base. So we say this is an acid, and you can say why is that? It should line up with one of these three theories, either Arrhenius, a Bronsted-Lowry, or Lewis. And we'll talk about how those three are different and what they mean right on out. So if it's an Arrhenius acid, so Arrhenius was a former scientist that he classified acids as something that increases the hydrogen concentration. Increase the hydrogen ion concentration. So for example, HNO3 nitric acid is added to water, and this hydrogen here is going to come off of the nitric acid and bond to and be floating on. So I increase the concentration of my hydrogen ion. So I have a hydrogen ion, I have nitrate, and I have water. Or if you think back to when we first did this, we had two waters that ionized. The ionization of water formed hydronium. So in this case, nitric acid is going to take this hydrogen and add it over to here, and you're going to get hydronium plus nitrate. So because acids increase the hydrogen concentration, his definition for a base is one that increases the hydroxide concentration. So we have sodium hydroxide mixed with water. We get sodium plus hydroxide plus H2O. So that is an Arrhenius acid and an Arrhenius base. Bronsted and Lowry were two different people that worked together and worked on acids and bases and worked in chemistry, and so they formed their own idea, and so we call it the Bronsted-Lowry definition of acid and a base. So Bronsted-Lowry acid is a molecule that is a proton or hydrogen donor, and so remember the Arrhenius increased the hydrogen concentration. Bronsted-Lowry is just a proton donor. Essentially, it's the same thing, but just worded a little bit differently to make life confusing. So for example, if we take NH3, which is ammonia, and we add it to hydrochloric acid, this H in hydrochloric acid is going to come over and join ammonia. And you're going to get this substance here, which is ammonium. So in this case, HCl is going to be your acid because it donated the hydrogen to ammonia. You can also have water actually can act as an acid. So in the case of you adding ammonia to water, a hydrogen from water is going to come over and join with ammonia to form ammonium again. So this is the same substance formed in the previous example. And then, so this is showing you your same situation, same exact thing going on. When this happens, when you get ammonium, ammonium now becomes an acid because it can donate that proton back to the hydroxide to form water again. So in this case, water is the acid when we have this situation. In this situation, ammonium would be your acid. And they can flip. Bronsted-Lowry bases. A base is a molecule that acts as a proton acceptor. So acids donate protons, bases accept protons. So it takes on the hydrogen ion. For example, again, we had HCl plus NH3 produces NH4, which is now our acid, and Cl is going to be our base because this accepted our proton. This was the base and this was the acid. It had one to donate. When they go to this side, this now has an extra hydrogen to donate. It becomes an acid. And Cl, a chloride ion, is a base because it can accept that ion. So that's an example of Bronsted-Lowry base. When you have an acid-base reaction, all you are doing is transferring protons from one molecule to another. In a Bronsted-Lowry acid-base reaction, you're taking protons from one molecule and transferring it to another. For example, water and ammonia. Again, hydrogen is going to go to the ammonia, producing ammonium plus hydroxide. So on the flip side, we could take this hydrogen and donate it back over to here, and we could get our initial reactants there. So that's a Bronsted-Lowry acid and base. The last person that classified them was Lewis. And he had a different way to go about classifying them. So Bronsted-Lowry both dealt with protons, whether it was concentration or accepting and donating. Lewis acids. Lewis classified acids as atoms, ions, or molecules that can accept electrons. So hydrogens have a positive charge, so they can accept an electron. So Lewis classified acids as atoms, ions, or molecules that accept electron pairs. Bases, those electrons had to come from somewhere, so bases donate electron pairs. So his definition is a little bit different. But when you have a Lewis acid-base reaction, you create a covalent bond between your electron donor and electron acceptor. For example, we have this situation here that you are combining these two substances to form this substance by this covalent bond right here. And so this is our covalent bond, which is formed from these two initial reactants. We can also have, so a fluoride ion can be added to bromine trifluoride to produce our product over here, which is again held together by covalent bonds. In terms of acids and bases, any acid, based on classification, anything that's classified as an acid is a Bronsted-Lowry acid. Not every base is going to be a Bronsted base because remember, your Bronsted-Lowry bases were they're hydrogen acceptors. So every acid is going to be a hydrogen donor, a proton donor, but not every base is going to be a hydrogen acceptor. Okay? And then, so to summarize, to give you these three as a real quick, these are the three. Your Arrhenius acids are anything that increases your hydrogen concentration. So if you want to write down just your three, make a list that you have acids, and you have Arrhenius here. Increases hydrogen concentration. So increase your hydrogen concentration. If you have a Bronsted-Lowry, which is called Bl, it donates a proton. Donates a proton, and then Lewis acids. Whoops. Lewis acids accepts electrons. If you want to make just a quick little table, that works really nice. For bases, I'll do bases down here. So again, Arrhenius, let me put ARR, is something that decreases the hydrogen concentration. For Bronsted and Lowry, they accepts protons. So instead of donating the proton, it accepts protons. And Lewis donates electrons. Those are your three classifications of acids and bases. So just a couple more things, then we'll be done for the day. But strong acids. we have strong acids, we have weak acids, we have strong bases and weak bases. Your strong acids ionize 100% in water, so they completely dissociate into their respective ions, and these create strong electrolytes. All strong acids are strong electrolytes. If you think back, remember, electrolytes are substances that conduct electricity when dissolved in water. So all of your strong acids form strong electrolytes and are good conductors of electricity when dissolved in water. Weak acids don't ionize at 100%. They form weak electrolytes, which do some partial conduction and create a reversible reaction, which we haven't looked at yet, but will in the future. There are 7 strong acids. So I will ask you to know these 7 strong acids. And everything else that is an acid is a weak acid. So you need to know hydroiodic, hydrobromic, and hydrochloric are your binary strong acids. Those 3. Your other strong acids are perchloric, sulfuric, chloric, and the last one that's not on this table is nitric acid, is also a strong acid. Which produces H3O and nitrate. So nitric acid is also a strong acid. So these are your 7 strong acids that you have to know. Everything else is a weak acid. Okay, and then if we look at bases, so a strong acid completely dissociated, a strong base also completely dissociates into hydroxide ions and your alkali, your base part. So for example, sodium hydroxide is a strong base. It completely dissociates into sodium and hydroxide. And your strong bases, if you look at this list, you have sodium, potassium, rubidium, and cesium. These are all found in column 1 on the periodic table, which are your alkali metals. Calcium, strontium, and barium are your alkaline earth metals. So your alkali metals get their name because of this property. So these are your strong bases. You'll need to know those as well. Here are some questions for you to answer, kind of going in tomorrow to get you thinking and refresh everything. And then I will see you next time. Thank you very much for your time and attention.